Okay, in today's class we will develop a finite element formulation for 2 node beam element. Before we proceed with that, let me summarize what we have done in the last class. In the last class we derived the governing differential equation for beam bending problem, and we also looked at while deriving this we also looked at various sign conventions that we adopted, that is for the nodal degrees of freedom and applied forces and moments and internal moments and shears, and these sign conventions are very important because the entire equation or subsequent calculations will be based on these sign conventions. And we also, while deriving this governing differential equation for beam problem, what we did is we used in conditions of equilibrium, that is sum of all forces in the transverse direction is equal to 0 and sum of all moments taken about a point is equal to 0, and we got the relation between the shear force and the applied load and also bending moment and shear force. And so in a way we can find what is the relation between bending moment and applied load. And after that what we did is we used assumed that these transverse displacements are small, and is based on the assumption that plane sections remain plane, we derived the relation between the displacement in the y direction, in the x direction, sorry, displacement in the x direction, and the relation between displacement in the x direction and the transverse derivative of transverse displacement. And then we derived strain, what is the relation between strain and transverse displacement, and then we used Hooke's law and got the relation between stress and strain. And then using the condition that are taking moment equilibrium about a cross section, we developed the relationship between bending moment and transverse displacement. And once we got this relation, we can substitute what is the relation between bending moment and load applied, and through this we got the governing differential equation. And it turns out that this governing differential equation for beam bending problem is a 4th order differential equation. So we require 4 boundary conditions to solve this problem, and these boundary conditions can be a combination or of any of the 4 boundary conditions, that is the transverse displacement, rotation, and bending moment, shear force. And here I want to emphasize that rotation is nothing but first derivative of transverse displacement, and bending moment is nothing but second derivative of transverse displacement multiplied by modulus of rigidity or EI. And shear force is related to third derivative of transverse displacement, and it is equal to EI times third derivative of transverse displacement with respect to the spatial coordinate, which is x. So now with that what we did is later we applied variational formulation or variational approach, and we got equivalent functional. And while deriving this equivalent functional, we applied integration by parts twice because beam bending differential equation is 4th order differential equation, and also we substituted the relationship between transverse displacement and shear force and transverse displacement bending moment, and also we used variational identities, and we derived equivalent functional, which is going to be the potential energy for beam bending problem for 2 conditions. First is essential boundary condition specified and natural boundary condition specified, and this equivalent functional turns out to be potential energy for beam bending problem. And potential energy, as you know, it is nothing but strain energy minus work done by the applied forces. Here strain energy is nothing but bending strain energy, beam bending strain energy, and work done by the applied forces are nothing but work done by the distributed loads and work done by the point loads, moments and forces. So that is what we have covered in the last class related to this beam bending. So in today's class what we will do is we will develop a finite element beam 2 node beam finite element for later computational purposes. So essential boundary conditions for a beam involves as you know it is transverse displacement and rotations, both of them specified at the ends, and so the trial solution must satisfy these boundary conditions. In finite element this can be easily done if both transverse displacement and rotations are chosen as independent degrees of freedom for each node. So a simplest element, which is a 2 node beam element, has 2 degrees of freedom per node. A 2 node straight beam element is shown here in this figure, and here EI is assumed to be constant over the entire length of the beam element, and also applied load along the element length is uniformly distributed. So Q is uniformly distributed and EI is assumed to be constant, and this will be using these conditions at the end when we are deriving when we are trying to simplify the stiffness equation and also load vector. So now to develop this shape functions and other things, it is convenient to define a local coordinate system as follows. Here you have 2 nodes in the x coordinate system. Node 1 corresponds to x is equal to x1 and node 2 corresponds to x is equal to x2, and the degrees of freedom at node 1 are v1 theta 1, that is transverse displacement and the derivative of transverse displacement, and the degrees of freedom at node 2 are v2 and theta 2, and this entire length, that is x1 to x2, is mapped on to another coordinate system in S, where s is equal to 0 corresponds to x1, s is equal to 1 corresponds to x2. So the relation between x coordinate system and s coordinate system is given by s is equal to x minus x1 over length of the element, which is nothing but x2 minus x1, and this relation, that is s is equal to x minus x1 over L, that is obtained similar to what we how we arrived for the bar element, that is we use linear interpolation formula, that is y minus y1 is equal to y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. We use that relation similar to what we did for bar element, 2 node bar element. So see, using that relation we get the relationship between s coordinate system and x coordinate system. Once we got this relation, we can find what is ds, a small differential element of length ds in s coordinate system, how it is related to a differential element of length dx in x coordinate system, that is given by ds is equal to 1 over L dx, and that can be rearranged in the manner dx is equal to L times ds. So suppose if there is an integral going from x1 to x2, and if you want to change the limits of integration to 0 to 1, that is x1 corresponding to 0, x2 corresponding to 1, then the integral which we need to integrate with respect to x, that is dx term in that integral we can replace with L times ds when we change the limits of integration from x1 x2 to 0 to 1. Okay, so in terms of s, element goes from 0 to 1, that is what I just explained, and since here at each node you have 2 degrees of freedom, and total 4 degrees of freedom are there. So we need to choose a cubic polynomial, and a cubic polynomial is an appropriate trial solution. If you recall, for when we are deriving bar element with 2 nodes and with 1 degree of freedom at each node, what we did is, since we have 2 degrees of freedom total for 2 node bar element, what we did is we started out with a linear trial solution. So depending on the number of degrees of freedom, if you have n number of degrees of freedom, it is better to start out with a trial solution having n minus 1 order or degree. So that is what is done here. Since there are 4 degrees of freedom, we are starting with a cubic polynomial for trial solution. As we did for bar element, we start out with this kind of polynomial. V is equal to a0 plus a1 s plus a2 s square plus a3 s cube. So now our job is to find a0, a1, a2 and a3, and back substitute these a0, a1, a2, a3 into this equation and group the terms containing the coefficient v1 theta 1, v2 theta 2, and whatever is left in the brackets, that turns out to be the shape functions or interpolating functions for this beam element. And while deriving these beam element shape functions, we are using both transverse displacement and rotation, and these kind of shape functions are called Hermite shape functions. So now let us start. And what is it theta? Theta is nothing but derivative of transverse displacement with respect to x. So using chain rule, dv by dx can be written as dv ds, ds dx, and we just learned that the relation between dx and ds is dx is equal to L times ds. So we know what is the ds over dx, which is going to be 1 over L, and v is already given in terms of s. So one can easily take derivative of v with respect to s. So dv over dx can be obtained. So now at each extreme point, that is at s is equal to 0, which corresponds to x1, we know what are the degrees of freedom. Transverse displacement is v1 and derivative of transverse displacement is theta 1. Similarly, at the other extreme end, which corresponds to s is equal to 1, which is nothing but x2, we know what is transverse displacement, and also we know what is the derivative of transverse displacement, which is which are v1 and theta 2 respectively. So we will make these substitutions. So now let us say at s is equal to 0, substitute at s is equal to 0 in the previous equation, that is v is equal to a0 plus a1 s plus a2 s square plus a3 s cube. In that you substitute s is equal to 0, will be ending up getting a0 is equal to v1, and next we need to substitute at s is equal to 0, derivative of v with respect to x is equal to theta 1, and when you do this substitution we get a1 is equal to L theta 1. So the unknown coefficients, out of unknown coefficients a0, a1, a2, a3, we already obtained what is a0 and what is a1 by these two equations. Now let us substitute the other condition, that at s is equal to 1, v is equal to v2, substitute s is equal to 1 in the equation, v is equal to a0 plus a1 s plus a2 s square plus a3 s cube, and then we obtained this equation, which is a2 plus a3 is equal to v2 minus v1 minus L theta 1, And similarly now what we need to do is we need to substitute s is equal to 1 in derivative of v with respect to s x, and which is equal to theta 2, and substituting s is equal to 1 in derivative of v with respect to x, we get this, and equating it to theta 2 we get this equation, which is 2a2 plus 3a3 is equal to L theta 2 minus L theta 1. So we got two equations in terms of a2 and a3, and we have two unknowns to be determined, which is a2 and a3. So we can solve these two equations and get a2 a3 in terms of v1 v2 theta 1 theta 2 and L. So if you solve these two equations for a2 and a3, we get a2 to be this one, a2 is equal to minus 3 v1 minus 2 L theta 1 plus 3 v2 minus L theta 2, and a3 as 2 v1 plus L theta 1 minus 2 v2 plus L theta 2. So we got all the coefficients a0, a1, a2 and a3 in terms of v1 theta 1, v2 theta 2 and L, which is the length of the beam element. Now what we need to do is we back substitute all these coefficients a0, a1, a2, a3 into the equation v is equal to a0 plus a1 s plus a2 s square plus a3 s cube. Substituting a0, a1, a2, a3 into the trial solution, we get this one. Now rearranging this equation such a way that we group all terms having v1 as coefficient separately and theta 1 as coefficient separately, v2 theta 2 as coefficients in the same manner separately, we can rewrite this equation in this form. So whatever is acting like a coefficient to v1, it is nothing but n1, and whatever is acting like a coefficient to theta 1, it is nothing but n2, and whatever is acting like a coefficient to v2 is nothing but n3, and whatever is acting like a coefficient to theta 2 is nothing but n4. So with this understanding, we can write this equation in a matrix and vector form by defining n1, n2, n3, n4, which are going to be the shape functions or interpolating functions for this 2 node beam element in this manner, and which can be compactly written as n transpose d. Please note that the n vector is defined as n1, n2, n3, n4, whereas earlier for bar element it is defined as n1, n2. So at each stage you should be checking what the shape function vector corresponds to, so to avoid confusion, and the displacement vector d consists of transverse displacement and rotation components at node 1 and node 2, that is v1 theta 1, v2 theta 2. As I mentioned, n1, n2, n3, n4 are nothing but shape functions or interpolating functions, and if we write these separately, they look like this, and it can be easily checked that n1 is equal to 1 at s is equal to 0 and n3 is equal to 1 at s is equal to 1. And if you plot these shape functions by normalizing n2 and n4 with respect to L, that is the equation corresponding to N2 is divided on either side with L. So then it becomes a function of S alone. So we can plot how these shape functions look like when S goes from 0 to 1. So this plot shows how shape functions vary with respect to S, that is S going from 0 to 1. You can easily observe that N1 is equal to 1 at S is equal to 0, N3 is equal to 1 at S is equal to 1, and N2, N4 are normalized with respect to L. So we learned that the trial solution V now can be written as N1 V1 plus N2 theta 2 sorry N2 theta 1 plus N3 V2 plus N4 theta 2. So now we are ready to find the derivatives of trial solution which are subsequently required for deriving the element equations. What is derivative of V with respect to transverse displacement with respect to x? Using chain rule we can write like this: dV over dx can be written as dV over ds, ds over dx, which can be written as 1 over L dV ds. Substituting what is dV ds, we get this relation. While arriving at this relation, V is equal to N transpose D, that is substituted, N1, N2, N3, N4 values are substituted, and D is nothing but V1 theta 1, V2 theta 2. So after making this substitution and taking derivative with respect to S, we get this relation. And what is the second derivative of transverse displacement with respect to x? Taking one more time derivative of this, second derivative of transverse displacement with respect to x can be written as derivative of V, derivative of theta value, that is which is nothing but derivative of transverse displacement. So using chain rule this can be written in a similar fashion as we did in the previous equation, and finally we get second derivative of transverse displacement with respect to x as 1 over L square d square V over ds square. So now substituting what is V, which is N transpose D, and noting that the nodal values, which are nothing but V1 theta 1, V2 theta 2, are constant when we are taking derivative with respect to S. So taking second derivative of shape functions, we get this relation. And if you recall, while deriving the relationship between bending moment and transverse displacement, we noted that bending moment is nothing but second derivative of transverse displacement times modulus of rigidity, which is EI. So bending moment is equal to EI times second derivative of transverse displacement, and now we obtain what is the transverse displacement relation once we know the nodal values V1 theta 1, V2 theta 2, and if you observe this equation, and it turns out that this equation is linear. So whatever two node beam element that we just developed, that gives us that captures bending moment accurately if the variation of bending moment is linear along the element length, because S is going from 0 to 1, and this relation, that is second derivative of V with respect to x, can be compactly written as B transpose D, where B is defined as the first row vector along with 1 over L square, and D, as you already know, D is nothing but V1 theta 1 V2 theta 2. But if you recall, in the potential energy we require square of V, second derivative of V with respect to x. So we require square of second derivative of V with respect to x. So that can be written, because second derivative of V with respect to x is a scalar quantity, we can write this as V second derivative of V with respect to x transpose second derivative of V, and we just noted that second derivative of V is nothing but B transpose D. Substituting that, we get square of second derivative of V as D transpose B B transpose D. So now we are ready, we got all the we got the trial solution in terms of finite element shape functions, and also we just obtained what is second derivative of V and square of that in terms of finite element shape functions. So now the next step is to substitute the trial solution, all these quantities, into the potential energy equation that we derived. And we learned that potential energy is nothing but strain energy minus work done by the applied forces, and the strain energy here corresponds to beam bending strain energy, and which is we already derived this, it is nothing but this u is equal to half integral x1 to x2 ei times second derivative of V with respect to x square times dx. As I mentioned earlier, we can change the limits of integration from x1 x2 to 0 to 1 in S coordinate system, and by making that substitution, that is x1 is equal to 0, x2 is equal to 1, and dx is replaced with L times ds, and ei is modulus of rigidity, and substituting what is the second derivative of transverse displacement, square of that is D transpose B B transpose D, and noting that D vector, which is nothing but V1 theta 1 V2 theta 2, they are independent of spatial, or they are not functions of S, noting that we can take them out of the integral and we can write in a compact form this bending strain energy, which is denoted with U there as half D transpose K D, and now K is defined as integral 0 to 1 ei B B transpose L ds, and is known as beam element stiffness matrix, and this is a general equation, and even if modulus of rigidity is not constant, this equation can be used and integrated, and we will get the stiffness matrix. Now work done by the distributed load, that is given by, we already derived this equation also earlier, WQ is equal to, that is W is because of distributed load Q, that is why subscript Q there. So WQ is equal to integral x1 x2 qv dx. So changing the limits of integration, x1 is replaced with 0 and x2 is replaced with 1, dx is replaced with LDS, and V is substituted, V value in terms of shape functions N transpose D, and noting that D is independent of S, it is taken out of the integral, and the entire thing WQ is compactly written as D transpose RQ, where RQ is defined as integral 0 to 1 Q N L ds. this is equivalent nodal load vector, and here this equation is also a general equation. Even if q, the distributed load, even if it is function of x or function of spatial coordinate, that can be included inside the integral and integrated, which gives equivalent nodal vector. So the previous equation and this equation are general equations which are applicable even if E, I and Q are functions of spatial coordinate. Now work done by the concentrated forces and moments which are applied at the extreme points of the 2 node beam element, which are nothing but nodes, is given by, it is nothing but force times displacement and moments times rotation, and this can be compactly written as d transpose Rf, where Rf is just compresses of all the forces and moments. F1 m1, F2 m2 is a vector of applied nodal forces. So potential energy pi can be written by substituting U Wf, that is work done or work done by the concentrated forces, which includes forces and moments, loads and moments, and Wq, which is work done by the applied distributed forces, is given by half d transpose Kd d transpose minus d transpose Rq minus d transpose Rf. Now applying the stationarity condition, and if you recall, we got potential energies here is nothing but equivalent functional in variational approach. So variation of this functional should be equal to 0, and which is nothing but partial derivative of pi with respect to the unknown parameters, which are here d, partial derivative of pi with respect to d gives us element equations. Finally we get element equations from stationarity of the functional. Please note that this equation or these equations are applicable to any beam element regardless of how modulus of rigidity Ei and Q vary along beam length. Once these values, that is Ei and Q, are specified, numerical integration can be carried out to obtain element equations. We will see what is numerical integration in a while or in the later classes, but we will see a specific case, because we started out assuming that modulus of rigidity Ei and Q are, modulus of rigidity Ei is constant and Q is uniformly distributed load over the entire element. So we will take that specific case when Ei and Q are constant, and then what we can do is we can explicitly write what is the stiffness matrix and what is the load vector, because Ei, once we take out Ei, integrand becomes very simple and we can easily integrate it manually. So by integrating this equation, we get this, or multiplying those two vectors we get this, and now integrating all the components we get this one. If you recall from your matrix analysis of structures course which you must have taken, and this is the kind of stiffness matrix that you arrive even using matrix and any of the matrix methods, and the same thing we obtained using starting with a finite element beam formulation and also starting with variational approach, we derived the potential energy equation and then we substituted transverse displacement, derivative of transverse displacement in terms of finite element shape functions, and finally after simplifying we arrived at this one. And this is a symmetry, the stiffness matrix is a symmetric matrix and all the diagonal terms are always positive. So here only upper triangular part is shown and lower triangular part is nothing but reflection of that, and we can also simplify RQ, assuming now to be Q to be constant, you can take that out of the integral Q and integrate the rest of the terms, we get this. And RF is already, there is no need of integration for RF because RF is already given as, or RF is already obtained as F1, M1, F2, M2. So the finite element equations for a prismatic beam element that is constant, having constant modulus of rigidity or EI with uniformly distributed load on the span and concentrated forces and moments applied at the nodes is given by this one, KD equal to RQ plus RF, or if we expand or if you substitute what is K, what is D, RQ, RF, this is how it looks. And now let us look at we obtain what is RQ, which is QL over 2, QL square over 12, QL over 2 minus QL square over 12, and what is the physical interpretation of this load vector or equivalent nodal loads. And please note that this is a sign convention that we are using for nodal degrees of freedom and applied forces and moments. And with this sign convention for the 2 node beam element, we obtained for a constant value of Q, that is uniformly distributed load, we obtained load vector to be this one, or the equivalent nodal loads at nodal loads here includes loads and moments at node 1 as QL over 2 and moment as QL square over 12 and QL over 2 minus QL square over 12. And here if you see, it is not just enough to remember or look at this vector as it is, but we should also make a note of what is the sign, what is this positive negative means. So here positive negative means whatever we are using this based on the sign convention, that is for nodal degrees of freedom, applied moments, applied forces and moments. Following that convention, this is the vector we got. Now let us consider a fixed end beam subjected to uniform upward load. The solution for this problem is well known and is presented in most elementary mechanics of deformable body textbooks, and here the figure shows fixed end beam subjected to uniform upward load Q along with the end moments and shear forces obtained using any of the solution procedures that are given in elementary mechanics of deformable bodies textbooks. And now all the forces and moments are indicated for this fixed end beam subjected to uniform upward load. So following the sign convention for nodal degrees of freedom, applied forces and moments, all these forces and moments on this fixed and uniform fixed end beam with uniform upward load q, all the moments and forces we can write in a vector like whatever is shown there, that is minus QL over 2, because if you see this fixed end beam at the left end, the shear force is acting in the negative direction to the sign convention, that is why minus QL over 2, and again at the left end moment is QL square over 12, which is acting in a negative direction if you follow the sign convention for the applied forces and moments. So it is going to be minus QL square over 12, similarly the rest of the quantities. Now if we compare this, comparing the moments and shears with equivalent nodal loads, it can be observed that in both vectors the magnitude is same, except that the sign is opposite. Wherever minus sign is there, here for fixed end beam at that location we have positive moment, wherever a positive moment is there or positive value is there, we get a negative value here in this fixed end beam case. So the physical interpretation, a physical interpretation is useful in developing equivalent nodal load vectors. So what is the physical interpretation? Physical interpretation is the finite element equivalent nodal loads are simply fixed end forces with sign reversed. So if we have a distributed load, instead of finding equivalent nodal vector, instead of finding equivalent nodal loads using finite element shape function substitution and doing all the integration and all that kind of stuff, if we know directly for that corresponding span, if you know this fixed end moments and shear, we can put them in a vector form and we can reverse this sign, that gives us the equivalent nodal loads for finite element calculations. So this physical interpretation is useful in developing equivalent nodal load vectors for more complicated distributed load patterns. Formulas for fixed end forces are available in already existing handbooks. Using these formulas, the equivalent load vectors can be written directly without going through the integration. Not only that, this physical interpretation will be using this when we are actually look at a method called superposition method in the later part of the lectures. So now this is about physical interpretation of equivalent nodal loads. So in summary, finite element equivalent nodal loads are simply fixed end forces with sign reversed. And now once we calculate for the nodal values, that is V1 theta 1, V2 theta 2, or what we do is usually to analyze any beam problem, the element equations are written and then assembled in the usual manner depending on the element connectivity. Whatever element equations we derived, that using those equations you have to assemble for each of the element depending on how many number of elements are there, and then assemble these element equations to get the global equation system using element connectivity. The solution of global equation gives nodal displacements and rotations. So we get V1 theta 1, V2 theta 2 for each of the element. after solving for these nodal unknowns, element quantities such as bending moment and shear forces in each of the elements can be computed from shape functions. How we do that? Displacement, once we get V1 theta 1, V2 theta 2, we go back into the relation V is equal to n transpose D, where n is nothing but n1, n2, n3, n4. So into that we substitute V1 theta 1, V2 theta 2, then we get displacement at any point in the element where S goes from 0 to 1. So S is equal to 0 corresponds to one extreme point of the element, S is equal to 1 corresponds to the other extreme point of the element. So we can sweep over the entire element length and get displacement at any point in the element using this equation. Similarly, bending moment at any point in the element, once we calculate V1 theta 1, V2 theta 2, we can use this relation, that is bending moment is nothing but EI times second derivative of V with respect to x. Please note that second derivative of V with respect to x is nothing but B transpose D. So we get bending moment at any point in the element by using this relation, by sweeping from S is equal to 1 to S is equal to 0 to S is equal to 1. So if you just see this equation, and this is it is linear in S. So as I mentioned earlier, the 2 node beam element that we developed, that gives us accurate prediction of bending moment if the bending moment in that particular beam problem is linear with respect to the spatial coordinate. And now what about shear force? Taking one more time derivative of this, we get shear force at any point in the element is given by this. So once we know V1 theta 1, V2 theta 2, we can substitute into this equation and sweep from S is equal to 0 to S is equal to 1 to get the shear force value at any point in the element. So if you look at these two equations for bending moment and shear force, bending moment is linear and shear force is constant. If you see this equation, you can notice that shear force is constant, and from mechanics of deformable bodies we know that exact solution for a uniform beam subjected to concentrated loading involves constant shear and linear bending moment. So if you have a uniform beam, that is where EI is constant and it is subjected to concentrated load, we know that shear force is constant, bending moment is linear. So the 2 node element that we just developed gives exact solution when it is used to analyze prismatic beams, that is EI is constant and subjected to concentrated loads. What about if the beam is not prismatic, that is non-uniform beams? This particular element may not give exact solution. So in that case we have to use more number of elements per span for better accuracy. And also not only that, if we have distributed loads, we need to the solution may not be accurate and we may need to use some special technique, what is called superposition technique. Using superposition, exact solution can also be obtained for uniform beams subjected to distributed loading. Therefore analysis of continuous beams in which cross sectional properties do not change in span requires nodes only at the supports and under concentrated loads. So wherever concentrated load is there, better we have a node at that point. So whatever beam element that we looked at, it is applicable for prismatic beam subjected to concentrated loads, and if the beam is non-uniform and if we have distributed load, we may have to use more number of elements, that is one option. And for the case of distributed loads, the other option is we can go for superposition method, which we will be looking at in the later part of the lecture. And in the next class we will look at a beam problem, a continuous beam problem, in which is subjected to concentrated loads, and we will see how the 2 node beam element that we developed performs. Thank you.